Now we'll talk about the limiting reactant, which is one of the most important topics of this chapter. So here we still use an example we used before to describe the stoichiometry, and this time instead of a single-deck cheeseburger, we're going to use a double-deck cheeseburger. So recipe now is instead of 2 beef patties, now we have 2 beef patties in order to make a burger. Apparently, we see the recipe now is 1 set of buns with 2 beef patties with 1 slice of cheese in order to make 1 double-deck cheeseburger. Now here's the question. If we have 2 dozen buns, 2 dozen patties, 2 dozen cheese slices, how many double cheeseburgers in dozen can be made? As you may realize or recognize or calculate already, so we realize it is going to be 1 dozen double-deck cheeseburgers, because with the 2 beef patties for each burger, we can only make up to 1 dozen double-deck cheeseburgers, while we have rest like a buns or the cheese slice in excess. So we realize since the patty is used up, so production stops. In other words, patty limits the amount of double cheeseburgers. Okay, so now as we realize it is a patty according to this so-called equation, combination reactions we call it. Beef patty is a limiting reactant, so beef patty is the reactant that limits the production of the product. In other words, this is a reactant that makes the least amount of product. So in our example, obviously, patties becomes the limiting reactant. But here's the thing. How do we realize that a stoichiometric question is also a limiting reactant problem? How can we realize, how can we note this type of calculation? So here's the thing. I want you guys to look at what I have highlighted. So we got 2 dozen buns, 2 dozen patties, and 2 dozen of slice of cheese. As you may realize, buns, patties, cheese slice are all reactants. So once we know the amounts of 2 or more reactants, that leads to us to compare which reactants could limit the production. In other words, by reading a question, we need to realize how many reactants that we know the amount of. That becomes an essential clue for us to pick up the information about this type of calculation problem. Speaking of theoretical yield, this is the amount of product converted from the limiting reactant. Once I said converted, that means mathematically converted. That means 100% of conversion. So the theoretical yield in making double cheeseburger according to our recipe and the amount of each reactant, everybody knows it's going to be 1 dozen. Now, let's look at limiting reactant in chemistry. Limiting reactant is also called the limiting reagent. LR stands for this limiting reactant in our calculation later on. It's the reactant that limits the amount of product in a chemical reaction. We can use this reaction as an example to understand better about the definition of a limiting reactant. So question here is, how many moles of titanium can be made if 1.5 moles of titanium 4 oxide, TiO2, and 2 moles of hydrogen are used? As we check out this equation here, we realize the equation is balanced. So from a balanced chemical equation, we can realize the stoichiometry of this reaction is 1 mole of titanium 4 oxide is equal to 2 moles of H2, also equals to 1 mole of titanium. Now, remember, we have 1.5 moles of titanium 4 oxide and 2 moles of hydrogen. Both, as we realize, are reactants. So, since 1 mole of titanium 4 oxide can make 1 mole of titanium, so 1.5 moles of titanium 4 oxide could, here I say could because I'm not sure whether there's going to be this amount of titanium, which is 1.5 moles of titanium, can be made. Because it's a 1-to-1 ratio, so 1.5 moles of titanium peroxide should or could produce 1.5 moles of titanium. In the respect of hydrogen, as we realize, the molar ratio of a titanium metal and hydrogen is 1 mole versus 2 moles. That means with the 2 moles of hydrogen, it only produces 1 mole of titanium metal. Now we have 2 different amounts of moles of titanium. Which one we should pick? As we realized, okay, hydrogen runs out because it produces less amount. So since hydrogen runs out, when the reactant is gone, reaction stops. So we know the limiting reactant is hydrogen. It makes the least amount of product by conversion. And it is the reactant that runs out first. And since this is a limiting reactant, so limit the amount of titanium metal that's produced. Another function of a limiting reactant, as we can see, is it decides the amount of product that a reaction yields. So from all the calculation we realized, 2 moles of hydrogen can only produce 1 mole of titanium metal, not 1.5 according to titanium peroxide, because hydrogen runs out. So it decides the amount of product that the reaction should yield. And one last thing, when the limiting reactant is used up, runs out, reaction stops. That means whatever that is going to stay in the reaction form, what we call the reaction mixture. Before we leave this slide, there's one more thing I'd like to talk about here. People usually think about the limiting reactant as the reactant with the least amount. In certain consequences, in certain examples, yeah, that's true. But that's not, I repeat, not always true. As we point out in our slides, we realize hydrogen is a limiting reactant, but it has the more amount compared to titanium peroxide. So once we pick the limiting reactant, we need to look at how fast the reactant can be consumed during reaction, not just from the initial amount. So this is one thing I like to point out about the limiting reactant. We are looking for how fast the reactant is being used by the reaction. Now, as we see, according to our discussion, there's only 1 mole of titanium can be produced. So our theoretical yield, according to the definition, the amount of a product that can be made in a chemical reaction based on the amount of a limiting reactant should be 1.0 moles of titanium. Well, from this definition, one thing that we can make certain is theoretical yield is 100% conversion of limiting reactant to product. What does that mean? It means once we pick the limiting reactant, we should know the theoretical yield from the reaction, because by mathematically convert the amount of limiting reactant to the product using the concept of stoichiometry, we should calculate the theoretical yield. In other words, theoretical yield and the limiting reactant are 2 birds, and one single calculation can get these 2 birds. Theoretical yield, according to its name, it cannot be attained. That means we cannot get 100% of a product. That also be backed by the chemical principle, which we're going to discuss this in Chem 2 class. However, it can be approached to whatever degree that we want. For example, if we can reach the reaction with the theoretical, so with the yield of 99.9999%, which is very close to 100%, so we said it is 100% yield according to the rules of sig figs. Theoretical yield can also have a unit, so it can have the unit of mass or the unit of moles. Another concept of yield is actual yield. This is the amount of a product actually produced by the chemical reaction. Actual yield, just like a theoretical yield, it has the unit of mass as grams sometimes, or the unit of amount as moles. The difference between the theoretical yield and actual yield is what we can actually isolate it or obtain from the chemical reaction. During this process, we could lose some of the chemicals as a product, or the reaction can, like we discussed, never reach the 100% of conversion. So actual yield is usually given in our question, say how many grams of the product is actually obtained by the reaction or gained by the reaction, so on and so forth. So this is the one thing we can tell about what actual yield is from the question. The more important concept of yield is percent yield. Percent yield is percentage of the theoretical yield that was actually obtained in a chemical reaction. It has the chemical formula, which is actual yield divided by theoretical yield times 100%. Since both actual yield and the theoretical yield has the same unit, so they cancel, so percent yield doesn't carry any unit. One thing I like to point out, percent yield is more important than actual yield and theoretical yield are by themselves. That is because we can use percent yield to judge how good the reaction is being designed or how good the reaction can be carried out by experiment. So for example, I got 2 students I would like to hire for my research. So one student takes 10 grams of my reactant by making only 1 gram of the product. The other students used up 0.5 grams of my reactant, but he made 0.1 gram of a product. Which one should I hire? Obviously, it's the second, because according to the percent yield, that student give me 20% of yield. The first student only gives me 10% of yield. So percent yield is a more important concept in terms of yield than any other yield we have discussed. So I just want you guys to realize what the equation that represents the percent yield, actual yield divided by theoretical yield times 100%. The concept of limiting reactant, however, sometimes cannot be avoided if we have 2 or more reactants involved in a reaction. So say if I have A and B both as a reactant to form a product, and we cannot count the individual atoms so that we can make them perfect for the reaction, because those atoms are just too many, too small, too tiny for us to count, as we already discussed when we discussed the concept of moles. So even though we can make them as perfect stoichiometry as possible using balancers or whatever, in terms of number of atoms or molecules, there are always going to be one reactant that's in more than the other reactant during the reaction. So once we got the 2 or more reactants, it is always a limiting reactant problem. In other words, one reactant runs out before the other one does. So since this situation cannot be avoided, so what good of this concept of limiting reactant can bring to us? So this is another way we try to get this thing that's apparently not sounds too good to us, but we will try to make it useful for us. One good thing that can bring us about this concept of limiting reactant is to eliminate impurity product. So for example, the same reaction we have discussed in order to make titanium metals. So say if we make hydrogen gas as a limiting reactant, imagine what happened. So one reaction is finished, hydrogen as a limiting reactant is gone. So we have 3 substances left. Titanium oxide, titanium 4 oxide, titanium metal, both are solids, and steam water gas. And of course, we can blow away the water, so that leaves us 2 solids, form a mixture. What I like to point out here is if we have these 2 metals form a mixture, it is not worthwhile for us to purify titanium from such mixture because it costs even more money than react this reaction to redo this reaction. So can we design this reaction so that we can have a pure titanium instead? So now let's put this reaction together. So this time, instead of hydrogen, we can use titanium 4 oxide as a limiting reactant. Imagine if titanium 4 oxide is a limiting reactant, when reaction is finished, titanium 4 oxide is gone. We still have 3 substances left. Gaseous hydrogen, gaseous water, and solid titanium. If we blow away those gases, all we have left is titanium. Now our focus is how pure titanium can we get. And also, I'd like to point out, in industry, hydrogen is a lot more cheaper than titanium 4 oxide. So in actual chemical reaction, in manufacturing, we put 1,000 times more excess of hydrogen to react with titanium 4 oxide, so that we just hope after reaction is finished, we can get as pure titanium as we can get as possible. So we can save a lot of money in purifying titanium metals. All right, another good thing we can get from the limiting reactant is to reduce the expense of the reaction. So for example, people wonder why anti-cancer drug is so expensive. One of the reasons is for some drugs, we use platinum. Platinum is a noble metal, very expensive. Usually it's twice as more expensive as gold itself. So in order to make the best use of platinum, so we set platinum as a limiting reactant, hoping when reaction is finished, we do not have to worry about whether we have to recover platinum metal or not. In this way, so we can have quite a pure of this we call the platinum 4 bromide in order to get more reaction to go. Okay, so now we have the limiting reactant. So what is the excess reactant? Excess reactants is the reactant or the reactants in a reaction except for the limiting reactants. For example, as we already discussed, hydrogen is our limiting reactant, so titanium 4 oxide should be our excess reactant. I just wanted to point out here, the leftover excess reactant, because it's not a limiting, right? So once limiting is finished, it's gone. So we have a certain amount of titanium 4 oxide that's left. So we call it leftover. So leftover of this excess reactant stays in the reaction, forms a mixture with the product. So that is why in chemistry, we do not say product when reaction is done. We say reaction product mixture. Well, after all this discussion of the limiting reactant, theoretical yield, actual yield, percent yield, excess reactant, what is the math for this kind of a problem? So let's go back to look at this making burger problem one more time, try to figure out just what kind of math we can use to solve this type of calculation problem. Remember the question here, 2 dozen of buns, 2 dozens patties, and 2 dozen cheese slices. How many double cheeseburgers in dozen can be made? Of course, there's a various calculation. Okay, even in our textbook, we can convert one reactant to another, and by comparing the amount, so we should be able to know which is the limiting reactant, and then we can carry out a calculation for the product thereafter. But throughout the years, I think my approach probably becomes a little bit more practical than the way of calculation I just discussed before. My discuss is, remember, when we have this type of calculation problem, especially when we realize the limiting reactant, there's, I'm not saying always, but almost always a concept of theoretical yield associated to this question. Like, okay, how many double cheeseburger in dozen can be made. That actually is asking for the theoretical yield. If the theoretical yield is asked, we have to find a limiting reactant according to the definition. Remember? Because theoretical yield is 100% of the conversion of a limiting reactant. So keep that in mind. Theoretical yield and limiting reactant are closely associated to each other. So why don't we just try to figure out the theoretical yield, then from those yields to figure out what the limiting reactant is. I just want to let you know, if we want to pinpoint the limiting reactant should give us the least amount of a product. Now, let's look at this stoichiometry. According to this recipe, we understand it takes 1 dozen buns equals to 2 dozen for patties equals to 1 dozen of cheese slices equals to 1 dozen cheeseburgers. Remember, we have 3 reactants: buns, patties, and cheese slices. 3 reactants, again, we know their amount of. That is essential clue for us to realize this type of calculation problem, limiting reactant type of problem. Here, I just put up the answer as we already discussed before. Limiting reactant, as we already discussed, this should be patties. The theoretical yield should be 1 dozen double-deck cheeseburgers. Now, let's see just how calculation carry out to support our conclusion. Since we have 3 reactants, why don't we just assume each one was the limiting reactant? Don't worry about the other 2. We just simply assume the other 2 got enough amount, or way more amount to support our calculation. So say, what if buns was the limiting reactant? Or patties, or cheese? I just want you guys to know, we start off the reactant, each individual reactant. We're going to carry out 3 conversions. Okay, so from dozen of buns, according to stoichiometry, 1 dozen buns equals to 1 dozen burgers. So we know it could give us 2 dozen burgers. If patties were the limiting reactant, according to stoichiometry, 1 dozen burgers versus 2 dozen patties. So we got 1 dozen burgers. If we consider cheese slice was the limiting reactant, according to calculation, stoichiometry is a 1-to-1 in terms of dozens. So that's going to be 2 dozen burgers. Now, I want to let you guys to realize, for limiting reactant, we are going to pick the smallest amount of the product. Why the smallest amount of product? Because reaction stops as patties runs out. Right? So patty is our limiting reactant. So throughout the 3 different values of dozen burgers, we pick the smallest. This is our mathematics strategy by converting every reactant to the same product. So we will know which one we're going to pick and what reactant should be designated as the limiting reactant. Well, dozen can be replaced into the moles, as we already discussed at the beginning of the stoichiometry. So we can have, instead of dozen to dozen conversion, we can have a moles to moles conversion. So we just convert, like we discussed, the moles of each reactant into the moles of same product. From all the different values of moles of products according to these conversions, we just pick the smallest amount of product, call it as a theoretical yield. The one that gives us the smallest amount, we call it limiting reactant. Well, this is the moles to moles conversion as we call stoichiometry, of course. Okay. So we convert all the reactants to the one product in moles. so that we can pick the smallest amount. In reality, we cannot measure each of the reactant or product by moles. All we can do is measure them by mass. In other words, we can convert the moles of a product into the mass because we can measure them. And also we obtain the amount of the reactant from their masses. So instead of one step conversion for each reactant, now we have 3 steps of conversion for each reactant. I'd like to point out, we're going to continue the same way of calculation for every reactant. So that means not only we have multiple steps of conversion, we have multi-reactants to convert to. So this such conversion is what we call the mass mass conversion. So how are we going to determine the excess reactant? Well, for the excess reactant can be divided into 2 categories. One is called excess reactant, that is reactant. This is the amount that we can actually calculate from the limiting reactant as shown by this conversion, mass mass conversion. So we start with the limiting reactant, because once we realize which is limiting reactant, every other calculation can be based on it. So we can start with the grams if grams are known, or we can start with the moles. It doesn't matter if we know the moles. So we can start with either, and we can convert it to the moles of a limiting reactant using stoichiometry, or maybe we have to convert to the grams. But I just want you guys to realize, from limiting reactant, all we can get is the amount of excess reactant that is reacted, consumed with the limiting reactant. This is one thing I want you guys to remember, to realize. The amount of excess reactant we calculated from limiting reactant is the one that is being used up with the limiting reactant, not the one that's got left over. The one left over is something that we're going to see how we calculate in our calculation problem example later. Now let's look at our example problem. This is the one comprehensive example problem that covers pretty much everything that we have discussed so far. The stoichiometry, the limiting reactant, and the balance, only the importance about a balanced equation of the reaction. And also, the question also wants us to figure out how much of that excess reactant that's left over in question C and the percent yield in question D. Okay, so just how are we going to solve this problem? Let's try to answer question A. So in question A, it asks us to write a balanced equation for this reaction. As we read the question, chemical treatment of the zinc sulfide with oxygen, apparently these 2 other reactants, so that is zinc sulfide and oxygen, gives zinc oxide and sulfur oxide, those 2 other products, obviously. So according to our inspection method, so I'm going to choose zinc sulfide as the most complex formula because it has 2 elements that shows only once in either side of the equation. Like a zinc shows up once in zinc sulfide as a reactant, zinc in the zinc oxide once as a product. Sulfur, same thing, once in zinc sulfide as a reactant, once in sulfur dioxide as a product. So I put 1 in front of zinc sulfide, that leaves 1 as coefficient of zinc oxide, coefficient 1 for sulfur dioxide. Now we need to balance the coefficient of this reaction by figuring out the coefficient of O2 oxygen. So as we count the number of oxygen atoms from the right, 1 times 1. Okay, so we got 1 oxygen atom from zinc oxide. There are 2 oxygen atoms from sulfur dioxide. So adding all up, so we got 3 oxygen atoms. How are we going to make up 3 oxygen atoms from O2? We only take 3 halves of oxygen molecules because we only need 3 oxygen atoms. Apparently, we understand we cannot have fractions as coefficient in a balanced chemical equation to report, so we multiply this equation by 2. So we have a 2 zinc sulfide react with a 3 O2, yielding 2 zinc oxide and 2 sulfur dioxide. So that is what we have in question A. Oh, here, by the way, I try to hybrid the handout I give you before the spring break into the slides, so that I'm going to use those slides, those handout as a template to show you just how we perform this calculation stepwise using our approach. And as I can tell you at this moment, my approach is complicated as it may sound, but this is an approach that can get us to the bottom of any calculation problem, especially stoichiometric calculation problems. So I just want you guys to get used to my way of calculation first, then you can develop your own style. All right, so now question B. Remember, this is a question. If 10 grams of zinc sulfide is combined with the 10 grams of oxygen, what is the theoretical yield of each product in grams? First thing first, I want you guys to realize there are 2 pieces of information in this question. Remember when we said piece of information, number plus unit plus entity, right? So we got 10 grams of zinc sulfide and 10 grams of oxygen. So according to this 3-page handout of the flow chart I gave you guys, okay, I just copied line by line here. So remember, in the first page we have step 1. Okay, so the record and list every number with the unit and entity as given, and we label them as either reactant or product if the equation is given. Remember, question A is about balancing this equation, right? So we're going to write down the desired unit and the entity. So we got 10 grams of something, 10 grams of something, right? So as we fill them out, we got 10 grams of zinc sulfide, 10 grams of oxygen. And we're going to leave out, label those reactant and products in 1 minute. Let's get to the desired unit and entity. Remember, the question says, the theoretical yield of each product in grams. So the question wants us to get the grams of zinc oxide and grams of sulfur dioxide. Now, let's highlight and label these 4 substances. As we recall, zinc sulfide and oxygen are the reactants, and zinc oxide and sulfur dioxide are the products. Why are we doing this? I just want you to get this so that we realize this question gives us information about something and it asks for something else. Now, it gives us the amount. It gives us the amount of the reactant, not 1, but 2. What does that mean? Oh, I'm sorry. Of course, you already realized. I hope this is about limiting reactant, because remember, limiting reactant is the stoichiometric question about multiple reactants that we know the amount of. Okay, carry on. Remember, in that flow chart, that is a big block called phase 2 or step 2. This step where we can collect as many conversion factors as possible. Okay. There are total 5 steps that we will go through. First step, we write and balance the chemical equation if it is provided. I believe we have done that in our question A. Okay, so here I give you the guideline. So balance equation. Okay, so if we have this balance equation, remember coefficient becomes to the molar ratio. All right, so according to this balanced equation, 2 zinc sulfide, 3 oxygen yields 2 zinc oxide and 2 sulfur dioxide. So how are we going to write up the molar ratio? Remember, molar ratio is another name of stoichiometry. I prefer to call it molar ratio because it's more plain English than the stoichiometry, which is chemistry ideal, so terminology. So the molar ratio among all these 4 substances is 2 moles. Remember, stoichiometry is about the molar ratio, so we just insert the moles between the coefficient and the substance and lay them out as a stoichiometry. So 2 moles of zinc sulfide equals to 3 moles of oxygen equals 2 moles of zinc oxide equals 2 moles of sulfur dioxide. This is how we set up the stoichiometry. And by the way, I put the green box around this to let you guys to realize this is our first pool of stoichiometry, the conversion factors, because we can pick any of these 2 to set up a conversion factor. So if question wants the zinc oxide from zinc sulfide, so we just pick 2 moles of zinc sulfide equals to 2 moles of zinc oxide to form a conversion factor. So we can make as many conversion factors using stoichiometry as we want from this pool. Our second step in the phase 2 is collect any other conversion factors from density or concentration. Apparently, we don't have any. Okay, so we pass that step. Third step is to calculate the molar mass in grams per mole if mass is involved. What does that mean? Or if mass is involved? That means mass of something is given or asked. So for example, remember 10 grams of zinc sulfide, 10 grams of oxygen, those are given, right? So we have grams of zinc sulfide, grams of oxygen. So we get the molar mass of these 2. And for the zinc sulfide right here, so it's a 97. So it's a 97.45 grams per mole. And we write them into 97.45 grams of zinc sulfide equals to 1 mole of zinc sulfide. This time I want you guys to attach the entities. And because we have many molar masses, we need to know which molar masses is for what substance. So same reason, 32 grams of oxygen equals to 1 mole of oxygen. Remember, question also asks us for theoretical yield of zinc oxide and sulfur dioxide. So those grams of zinc oxide, grams of sulfur dioxide is what the question desired. So we get molar mass of these 2 as well. And here are the 4 more conversion factors we collected so far. So one way for us to recognize a stoichiometry question is the solution map is pretty much set. All we need to know, as I'll show you, as you remember early on when we went through the example problem in the stoichiometry. So solution map is pretty much there for us to choose. Okay. All we need is to find out enough conversion factors to support our calculation. All right, step 4 and step 5, since not the number of atoms or molecules are involved, so we pass that step. STP is about the gas chapter. We don't see any of this here, so we pass that. All right, so remember we got the 2 green boxes of the conversion factors we have collected so far, and we are about to use them. Step 3, our given and desired entity is the same. Apparently, after we label reactants and products, we realize question provides the amount of products, ask for the amounts of, give the amount of reactants, ask for the amount of product. So it's not about the same entity. So that is about the stoichiometry. Since it's a stoichiometry, sorry, I thought I deleted the animation here. All right, so as for stoichiometry, we realize that we got the solution map, okay, for one substance A or B according to here is going to be reactant, and we got another solution map for the product. Okay, and here, okay, so this is for gas, and we're going to see that in gas chapter 10. This is a liter of solution, which we're going to see that at the end of this chapter. This grams, moles, numbers, this is something we have discussed. Okay, so that is for substance A, that's for different substance. We can only connect these two solution maps through the moles. How do we connect them? Stoichiometry right here. Delta H is something that we're going to discuss in chapter 5 here, so don't worry about this portion. This portion is going to be discussed as we go chapter 5. Okay. All right. So, as according to this question, so we know the amount of zinc sulfide and oxygen. And here, okay, let's focus on zinc oxide at the beginning. And then once we get the zinc oxide, we will get the grams of sulfur dioxide as a second product. All right, so what are we going to do here? We are going to choose the solution map. And here's some tips, okay? So a solution map starts given unit and entity and ends at the desired unit and entity with the stoichiometry included. That means we have to have moles of given entity to moles of desired entity right in the middle of the solution map, as we already discussed in the previous calculation problem. Another thing I want to point out is number 3. If there are 2 or more given units in the entity labeled as a reactant, it is a limiting reactant question. Our strategy is convert each reactant to the same one product, usually desired entity. For example, zinc oxide. All right, so what is this solution map going to look like? First, we must understand that there are going to be 2 solution maps. First, for zinc sulfide to zinc oxide. Remember, we got the 10 grams, right? So we have 10 grams of zinc sulfide to moles of zinc sulfide to moles of zinc oxide to the grams of zinc sulfide. That is conversion from zinc sulfide to zinc oxide. Remember, we're not done. We also know 10 grams of oxygen here. So for 10 grams of oxygen, we start from here to moles of oxygen to moles of zinc oxide to grams of zinc oxide. So 2 solution maps. So that explains the step 2. Each given and or desired unit entity must produce a solution map. So we got 2 zinc sulfide and oxygen, 2 reactants, 2 solution map indeed. As we said, this is a limiting reactant problem because 2 or more given units entity labeled as a reactant, which we know the amount of. So 2 solution maps, as we already discussed. So from grams of zinc sulfide to the moles of zinc sulfide to the moles of oxygen, zinc oxide, and the grams of zinc oxide. And we do the very similar thing to from grams of oxygen to the grams of zinc oxide. All right, so I just want to point out right here. Okay. So now we get the different amount of grams of zinc oxide. Which one should we choose as theoretical yield? You got it. We choose a smaller amount. Right? The smaller amount is our theoretical yield. The one gives us a smaller amount is the limiting reactant. All right. So once we know the limiting reactant, remember as I said to you before, once we know the identity of the limiting reactant, we can start off the limiting reactant for the rest of calculation. So that means if we pick out whichever one, zinc sulfide or oxygen is limiting reactant, we can start with the grams of this limiting reactant, the moles of limiting reactant to the moles of soft oxide to the grams of oxide. That means we can skip our fourth conversions. Remember, once limiting reactant is known, we use limiting reactant for the rest of the calculation. So how many solution maps? 1, 2, 3. First 2. We find out what limiting reactant is and the theoretical yield for zinc oxide, and we get the limiting reactant and carry out the calculation in order to get the theoretical yield of grams of sulfur dioxide. Okay. So for the first solution map, there's no need for us to do it because once we know the limiting reactant, it's done. Okay. Last step, calculation. We carry out a calculation indicated by the solution map or maps from the step 4. We got 3 solution maps to carry out. So for our first, 10 grams of zinc sulfide, okay, to the moles. So moles of zinc sulfide on top. So this is a molar mass we use as a conversion factor. So 97.45 goes with the grams. So this at the bottom, we understand that's going to be division. And moles to the moles, that's a stoichiometry, right? So then first the green box, so we can pick zinc oxide, zinc sulfide to set up the conversion factor. Second, so the last one, moles to the grams, that's molar mass of zinc oxide. Grams on top this time, so number goes on top. So basically what we're going to need is we multiply everything on the top, divided by everything at the bottom, so we can have 8.36 grams of zinc oxide. I hope my calculation is correct. If it's wrong, so forgive me. As for the second conversion factor, so solution map, we start with the 10 grams of oxygen. Okay, again, molar mass of oxygen, stoichiometry of oxygen to zinc oxide as conversion factor. Finally, molar mass of zinc oxide. So we end up with 17.0 grams of zinc oxide. As you can see here, we have 2 different amount or masses of zinc oxide. Which one we should pick? Okay. Remember, smallest amount, right? So the theoretical yield for zinc oxide, we pick the smallest amount, so that's 8.36. We never pick the one with more because we are not going to get there. The reason is limiting reactant. Reaction stops because one of the reactant is out. All right. The reactant gives us the smallest amount should be the limiting reactant. So by calculating the theoretical yield of zinc oxide, we figure out what the limiting reactant as well. Remember, one stone, 2 birds. All right, so let's carry out our third solution map. Now that we know the limiting reactant is zinc sulfide here. Okay, so let's start with the 10 grams of zinc sulfide and carry out the calculation. So we find out this is 6.57 grams of sulfur dioxide. That is for the question B. A lot of calculation involved right here. As for question C, how much reactant is left over in grams? In order to answer this question, first, we need to recall what we have done in the previous calculation problem. Remember, in question B, we identify what the limiting reactant is, right? So if you recall, it is, you're right, zinc sulfide. So once limiting reactant is identified, we always use limiting reactant for the beginning of the calculation. So we know there's a 10 grams of zinc sulfide. What does question want? Remember, there are two reactants. One is limiting, the other one, of course, oxygen. So oxygen, which is called excess reactant, the question wants us to figure out is what's called left. All right, how are we going to get the amount of oxygen that's left over? Okay. Before we get that, let's go through the second step, collect the rest of the conversion factors. First, remember we have a balanced chemical equation. Okay, so we can pick the stoichiometry that's particularly for this question, because question wants the relationship between zinc sulfide and oxygen. So we just simply write up 2 moles of zinc sulfide with 3 moles of oxygen here. I just want you guys to realize it is the reacted. Okay, reacted. It is very important. The amount of the excess reactant we calculate from the limiting reactant is the amount that consumed or reacted with the limiting reactant. So we should recall the reactant. All right, so this is our first conversion factor we collected. Assume you realized, okay, so we got 10 grams of zinc sulfide, so molar mass of zinc sulfide. Grams of oxygen left over, decide according to this question. So we got a molar mass of oxygen. Okay, write them into the equation form. So 2 more conversion factors. I'm going to skip the rest because the rest do not apply. Okay, so in step 3, as we recognize, question asks for oxygen, which is different from zinc sulfide. So that's a stoichiometry question. So we set up a solution map. Okay, so once we set up a solution map, these are 3 tips I want you guys to go through, right? So for solution map, use the stoichiometry in the middle of the solution map. So this is part of a solution map. Okay, if we want to do it our own, okay, we got it at the flow chart. Okay, so moles of a given entity, so that means moles of what? Moles of zinc sulfide to moles of oxygen. So that is a part of the solution map that's already there, and all we have to do is finish the rest. Each given unit entity must produce 1 solution map. We got 1 given unit entity, so we understand that it's going to be 1 solution map. If 2 or more, we understand it does not apply. All right. So this is the stoichiometry, the first tip. So moles of zinc sulfide to the moles of oxygen reacted, and with the help of 2 conversion factors as molar masses, so we can get the grams of zinc sulfide to the moles and moles of oxygen to grams of oxygen that's being reacted. That is not what the question wants, right? The question wants us to solve the grams of oxygen that's left after the reaction is finished. So there's got to be the second equation that we have to find. And what's the second equation? Remember, we put in 10 grams. We put in 10 grams of oxygen as a total mass. And once we figure out the mass of excess reactant that's being reacted, we should be able to solve the mass of excess reactant easy. Right? 10 equals to whatever amount plus the mass of ER left over. So that is the very simple math. All right, so our focus here is to get the grams of oxygen that's reacted. Right, so we start with the 10 grams of zinc sulfide, okay, to the moles of zinc sulfide. So moles of zinc sulfide, the moles of oxygen is reacted, grams of oxygen reacted. So throughout the calculation, we figure out 4.93 grams of oxygen that is reacted right here. And according to this second equation, remember we put in total 10 grams, and 4.93 grams of oxygen is being reacted. So how much grams of oxygen is left? 5.07 grams. Because these two numbers adding up should give us 10 grams. So that is for question C. Question D here, it says suppose only 7.5 grams of zinc oxide is recovered. What is the percent yield of zinc oxide? Okay. When we call percent yield, so here's the formula, the equation for us to get percent yield. Percent yield equals the actual yield divided by theoretical yield times 100%. Okay. Speaking of theoretical yield of zinc oxide, remember we calculated somewhere, right? So in a couple of slides before, so we can go back and find out. So how do we recognize 7.5 grams? What is this? Okay. Remember, theoretical yield is what we calculated. So here, 7.5 grams has to be actual yield. So once we realize that, everything else is very simple. So the percent yield is 89.7%. All right, before we end this lecture, I just want you guys to realize how important it is for the 3-page handout I passed in the class. All right, remember this is our step 1. So this is our first step. Record, okay, label them, reactant and product, so we know whether there's going to be a stoichiometry problem. If we have a multiple reactants that we know the amount, that is a salt limiting reactant problem on top of stoichiometry. And we have 5 ways to collect conversion factors. Okay, so here I give you the detailed information. So once we have this, okay, so the density or concentration. So I give you the format how to write them into the equation form of this conversion factor. And third step, so this is the second step. This is our third step. So our given desired entity and desired entity, so our given and desired entity is the same. So if it is yes, okay, it's the same entity, remember. So we have different ways to do it. Sorry, if the answer is no, it goes through stoichiometry. By the way, there's also a very good tip we need to know. If you are giving a chemical equation, I would like to say 95% of the time it is a stoichiometry problem. Because our cognitive logics, what good it is for a chemical equation if it is not a stoichiometry problem. Right? It's pointless to provide an equation if that's not a limiting, if it's not a stoichiometric question. So there's a lot of ways to prove our skills. Okay, so that's one way that we need to realize. All right, so this is solution map, right? So solution map for how do we get a stoichiometry. So the solution map, a comprehensive solution map is right here. All we have to do, as already shown, so to pick from where to where. So from grams of substance A, so grams to the moles of substance B, to the grams of substance B. And of course, we can go to liters to moles to liters. We can go to, okay, so grams to the moles to the numbers. So we can have all kinds of methods. So calculation problems according to this. And of course, 3 tips. I just want you guys to know, okay, just how many solution map that is going to be required, Okay, so what kind of solution map we need to develop? Okay, first step tell us we use a stoichiometry embedded in our solution map. Okay, how many solution map that's going to be required is determined by so number 2 and number 3 here. Okay, number 3 is more important. Of course, if that's about the same entity, so we understand that it's only part of this, so grams moles the number, and we're going to discuss the liters of a solution on the next part of the lecture. Okay, so that is all for this portion of the lecture. Thank you for your time. Please let me know if you have any questions.